So far we've talked about inferential tests that you can use when you want to compare two means, whether the two means are both from different samples, or if you know a population mean and you compare it with a sample mean. But now we're going to talk about a more general situation where there's three or more means. Really, you could use it for two or more means, but usually you use this approach for three or more means. And we're going to start with what's called a one-way between groups ANOVA. And ANOVA stands for Analysis of Variance. And we'll see in a little bit why ANOVA is a great name for this statistical test. It's called a one-way ANOVA, the one we're going to start with, because there's only one independent variable. There's only one grouping variable. And later on we'll talk about when there's more than one grouping variable. And between groups just means that each person in your data set is in only one group. So you use a one-way ANOVA when you have one-way between groups ANOVA when you have three or more groups. Each participant is in one group, not in all the groups. When you don't know your population means or population standard deviations, which is usually the case when you're doing research, and you usually estimate these from your samples, which is what we're going to do in this case. And last, your dependent variable is scale. So it's an interval or ratio scale measure. And the example I'm going to use for a one-way between groups ANOVA will be our exams equally difficult in three classes. So let's say I'm teaching Intro to Psych, Stats, let's say I'm teaching Intro to Psych, Research Design or Research Methods, and Statistics. So I have different students in each of these three classes, and I'm going to compare the scores of the students on their exams to see if the exams are the same difficulty in all the classes or if one is harder than the others. And notice each participant is in only Intro or Research Design or Stats. If all the students were in all three classes, then we would use a different kind of ANOVA called a within subjects ANOVA. For this example, the null hypothesis, H sub naught, would be that the mean of the intro class is the same as the mean of the research design class, and those two are both also equal to the mean difficulty of the exams for the statistics class. So notice that this null hypothesis could be wrong in reality if any two of these means are different from one another. So usually you don't write a single alternative hypothesis like you did for a t-test. Here you could say for your alternative hypothesis something like any two means differ, because this is false if one or two are different from each other, two or three are different, or one or three are different. So you could also write it out that way if you want. You'd have like one alternative hypothesis is mu1 does not equal mu2. Another alternative hypothesis, mu1 does not equal mu3. And a third would be mu2 does not equal mu3. So if any of these are the case, then the null hypothesis is wrong. Now I'm going to go through the steps of a one-way between subjects ANOVA. So first off, we'll write out our null hypothesis. We'll start with an example where there's three groups. And the null hypothesis just says the means at the population level of those three groups are the same. If we had a fourth group, you just also add that as being the same. But we're going to start with the simpler version. And you can do that with any number of groups, but we'll start with the simpler version that only has three groups. And we'll stick with the example where we're looking at the exam difficulty for Introduction to Psychology, Research Design, and Statistics. So the null hypothesis says all three classes exams are equally difficult. The next thing we'll do is we'll draw the sample distributions. So these are the scores of the actual students, the observed students in my classes. So those are going to go down here. These are the observed sample distributions. And when you're doing research, right, this is the only data that you actually observe. SPSS does this top stuff behind the scenes, which is why it's important for you to see it and what's happening behind the scenes in a class like this. And then we'll say this is the Intro to Psych class, Research Design, and Statistics. And I kind of squished these axes in just to save some space. 80, 90, 100, 110, 120, we'll say intro students look something like this. And say the research design students look something like that. And the statistics students look something like that. And for the intro students, we'll say that their mean was 100, their standard deviation is 10, and their sample size is 33. And for research design, we'll say their mean is also 100, their standard deviation is also 10, and their sample size is also 33. And for the statistics class, we'll say their mean is 120, so it's higher than the other two classes, so the statistics exam seems to be easier. The standard deviation is 10, and the sample size is 33. I want to point out that I'm keeping the sample sizes equal across these three groups because it simplifies all of the math for doing this inferential statistical test. And by simplifying that math, it makes the actual logic of this test easier to understand. In a later video, I will explain the more complicated way to solve the one-way between subjects ANOVAs with unequal sample sizes. Our third step is going to be to draw the population distribution if the null hypothesis is true. So if the null hypothesis is true, all the means are exactly the same as one another. And also, this test assumes the variability of these three populations, the one for introductory psych, research design, and statistics, are all the same, right? And so we actually have three estimates of this one value because they're all the same, so we could just call that one there. So this is the null hypothesis, population distribution, right? So these were individuals, individual students, individual. And these are going to be individuals as well. And this will be a normal distribution with a mean equal to whatever these three are. And really, you can think of it as three perfectly overlapping distributions if you'd like. And they all have the same mean. And they all have the same standard deviation. We don't know the mean, and we don't know the standard deviation, but the null hypothesis assumes that all these are, that they all have the same mean and that they all have the same standard deviation. And then what we're going to do is, assuming that those things are the case, we're going to figure out how likely is it that we have these three observed sample means due to random sampling from this null hypothesis situation up at the population level. So the next thing we're going to need to do is estimate the population standard deviation. And so we have three different estimates, one from each sample, and we're going to average them together. And because the sample sizes are all the same, that's really going to be easy. And one thing that's a little different with an ANOVA compared to a t-test is we're actually going to work with variances, analysis of variance. We're going to work with variances now more than standard deviation. So we're going to actually calculate the variance that's pooled across all three of these. So we're going to take our first group's standard deviation and square it to make its variance. Do the same with our second group, and do the same with our third group. And then we're just going to take the average of those. I'll say this is the number of groups. So we have 10, 10, and 10. 10 squared plus 10 squared plus 10 squared divided by the number of groups. There's 1, 2, 3 groups. So 10 squared is 100. 100 plus 100 plus 100 is 300. Divided by 3 is 100. So our variance estimate is 100. For an ANOVA, we actually have more than one variance estimate. And the one that we just created by using the variance of our three different groups is going to be called within. This is going to be the variance within. And it's called within because it's the variance within this group and the variance within this group and the variance within this group that have been pooled together to create a single estimate. So this is the variance s squared, the variance within. And the variance within is how much variability is expected if the null hypothesis is true. So if the null hypothesis is true, the amount of variability that we would expect is just the pooled variance within these three different groups. And so with a t-test, what we did is we created a sampling distribution down here, given a certain amount of variance or variability up here. And that told us the kind of sample means we would expect given this null hypothesis situation up top. It told us the kind of sample means we expect if the null hypothesis is true. And so it told us the kind of standard deviation across all the means. For an ANOVA, it's going to be kind of like that, but what we're going to end up doing is we're going to keep this population variance here. And again, that's how much variance you expect if the null hypothesis is true. And what we're going to do is we're going to see how much these three means vary and see if they vary more than expected based on the within groups variance. And how much these vary is going to be called the between groups variance because these means are between the groups. Group 1, Group 2, and Group 3's means. All right, so we've got our population distributions drawn, and we'll call this within, and it's our estimate based on our three samples. Next, we will draw the observed sampling distribution. Notice when we've done this in the past with t-tests, it was never the observed sampling distribution. It was always the sampling distribution assumed if the null hypothesis is true. So that's going to be a little bit different here. And notice this is the observed sampling distribution. In the past, we've always had the sampling distribution be the kind of sample means you expect if the null hypothesis is true. But now it's actually going to be the observed sampling distribution. So that's different than in the past. It is still going to be sample means. And in fact, it's the three means we observed in our three different classes. Right? So I'll put these here on this frequency distribution. So we need to have at least down to 100 and all the way up to 120. So 110. So there's 1 score, That's a 100, another score. That's a 100, and then a 120. So there's the 3 scores that we have on our sampling distribution, our observed sampling distribution. All right, the next step is going to be to calculate our test statistic, which in this case is an F statistic. And the F statistic is going to be equal to the variance estimate from between groups divided by the variance estimate from within groups. So first off, I just want to point out this bottom part here, the variance estimate within groups, is what we've already calculated. So this is how much variability we expect there to be if the null hypothesis is true. Right, and so this is based on, remember, it's just you take the 3 standard deviations of your 3 groups and you pool them together, you average them, and that's how you got this. Now what we're going to see is if the means of these 3 samples differ more than you would expect if we got our samples from this kind of a population. So this F statistic is different than a T statistic in that it's working with these variances up at the population level. So that means that what we're going to need to do is we're going to need to turn our sampling distribution into our estimate of how much variance there is up at the population level based on the data we have between our groups, between our 3 group means. So this is the variance estimate between based on our 3 group means. So to calculate our variance between, we're going to do the reverse of what we're familiar with. So what we're familiar with is taking a population with known characteristics because we're assuming the null hypothesis is true, right? Remember we took random samples of a certain size, right? We'll say 33, because that's what we're going to be using in this case. Right? We took a random sample of 33 individuals from that population. We calculated the mean. We plotted that down here. Right? And so we did that for one sample, and then we did it for another sample of 33. Calculated its sample mean and put that down here. And we kept doing that over and over and over for every sample of 33. And that's how we got our distribution of expected sample means. And remember, we had a formula where we could use the population standard deviation to determine what the standard deviation should be for the sample means. Right, so the standard error, which is just the standard deviation of sample means, had the formula S divided by the square root of the sample size. Remember, that sample size is the sample size you use for each of those samples when you're producing that sampling distribution. So what we're going to do now is we actually have 3 data points. So what we're going to do is we're going to calculate its standard deviation. And we're going to go up. So we need to modify this formula because we want to get the variance between, right? So we want this variance to be between. So I'm going to rewrite this over here. So we'll start off with the standard error equals S divided by the square root of n. All right, so we need to get this to be variance squared. So we're going to square both sides. So then we have SE squared equals S squared divided by the square root of n times the square root of n. So that's just going to be n on the bottom. And we need to get this variance by itself. So we're going to multiply both sides by n, and those will cancel out. So we end up with our variance between, because this is between these 3 group means, equals n times the standard deviation squared of this. Notice we can actually stick with the variances. We don't have to do any square roots now because we want a variance estimate rather than a standard deviation. So that's kind of nice. It saves us a little bit of extra work. All right, I'll rewrite this formula up here to create a little bit of room. So the first thing we're going to need to do is calculate the standard deviation squared, the variance, for these 3 group means. So the variance this is the standard variance formula that we've been using since our descriptive statistics part of this class. the scores, in this case there's 3 scores, there's 3 sample means, divided by the mean of those scores, divided by the degrees of freedom. And the degrees of freedom for these 3 scores is just like it would have been back when we were using any sample data to estimate a population parameter. Our degrees of freedom here, so we're going to call it between, degrees of freedom between, because we're looking at between groups, between these 3 groups. It's going to be the number of scores, we'll call it the number of groups because there's 3 groups, minus 1. All right, so to calculate the variance between groups, the first thing we need to do is calculate the variance of these 3 scores. So this is the variance, that's the same variance we were familiar with from the descriptive statistics part of this class. It's got the same old formula. We're just putting SE instead of S squared. All right, so it's down here. So we have each score, so there's 3 scores, their sample mean, so I put X bar here. And then the overall mean of those 3, let's call that X bar of X bar, divided by the degrees of freedom. So this is the exact same formula for variance from earlier in the class. So there's nothing different here. And our degrees of freedom is going to be just like it was before. We're going to call this degrees of freedom between, because it's between these 3 different groups. And it's going to be the number of scores minus 1. And in this case, we'll call n sub g for the number of groups. There's 3 groups, so it's going to be 3 minus 1 will be 2. All right, so we'll calculate this, the variance of these 3 scores. So the first one is 100. We need to subtract the overall mean, which I calculated as 106.67 squared plus the next score, minus the overall mean, 106.67 squared plus the last score, 120, minus the overall mean, squared divided by the number of groups, 3, minus 1. Okay, so the variance of these 3 sample means is going to be negative 6.67 squared plus negative 6.67 squared plus, that is 13.33 squared. That'll all be divided by 3 minus 1, which is 2. So negative 6.67 squared is 44.49. It's the same here because it's the same numbers being scored, 44.49. And 13.33 squared is 177.69. And all this again will be divided by 2. So we add up all those numbers on the top. We get 266.67 divided by 2. So our variance for these 3 scores is 133.34. Just right here. So our variance amongst the sample means is 133.34. All right, so we're halfway to figuring out our variance estimate for our between groups, which goes on the top of our F statistic. Right, we've determined that the variance of our 3 sample means is 133.34. Right, but this is from a distribution of sample means, and we need to go up back to a population, right? So we're going to do the reverse process of what we did before, and we've already calculated, or we've already determined that formula. So the variance between is going to be our sample size that we use to produce our sampling distribution, multiplied by the variance of that sampling distribution. So S squared B. So our sample size that we use to create our sampling distribution here is the sample size that's the same for all of our samples, 33. Remember, that's how we produce our sampling distribution, is all those samples have the same sample size. Multiplied by 133.34. And when you multiply those together, you get a nice round 4,400. So our variance estimate between groups is 4,400. So the kind of population that would have produced the observed sample means is not very similar to the kind of population that we're assuming if the null hypothesis is true. And notice that here I've kept things simple with our samples all having the same sample size. To calculate this, if your sample sizes are unequal, it's a lot more complicated. You use what's called the sum of squares method, and I'll show you that later on in another video. I'll have another video on that later. So now that we've calculated our variance between our observed variance, we can calculate our F statistics value, our F statistic for this data. So here our F statistic equals 4,400 divided by 100. So here we have an F statistic, or an F of 44. So I've rewritten our F statistic up here, and our next step is going to be to calculate our critical value, in this case our F critical value. Right, and this is the cutoff value where if our test statistic is more extreme, we're going to reject our null hypothesis. If we were using SPSS to do this analysis, instead what we do is it would tell us our p-value. And if our p-value is smaller than our alpha of 0.05, we'd reject the null hypothesis. But when we're doing these tests by hand, it's hard to calculate that p-value. And so instead what we do is look up our F critical value in a table, and there's a specific table for this, our F table, and that's what we're going to use when we're doing it by hand for a class like this. So the table that we have to get our F critical value asks for two kinds of degrees of freedom. It asks for F critical, it asks for the degrees of freedom between and the degrees of freedom within. The degrees of freedom between were those that we used here, right? And so remember that we had 3 sample means, the number of groups, minus 1. And this was the denominator in the formula we used to get the standard deviation, really the variance for these 3 sample means. So that was pretty easy to get. In this case, it would be, there's 3 groups, so it's 3 minus 1. The degrees of freedom between is 2. The degrees of freedom within is going to be the sum of the degrees of freedom for our 3 different groups. Remember, our variance within was this standard deviation and this one all pooled together, averaged together. So our degrees of freedom within is going to add up the number of degrees of freedom that went into this calculation with the ones in this calculation and the ones that went into this calculation. So it'll be the degrees of freedom 1 from this group plus the degrees of freedom 2 from this group plus the degrees of freedom 3, the ones from this group. To calculate this standard deviation, recall, we used a regular formula to do so. Our degrees of freedom is down here. Right, so this is the degrees of freedom for this group. This is degrees of freedom 1. So it's the number of individuals in group 1, 33, minus 1. So our degrees of freedom 1 equals the number of participants in group 1 minus 1. Our degrees of freedom 2 equals the number of participants group 2 minus 1. And our degrees of freedom 3 equals the number of people in group 3 minus 1. Because these were all the degrees of freedom used in the formulas to calculate these standard deviation. And in this case, each of our sample sizes is 33. 33 minus 1, 33 minus 1, 33 minus 1. So these are all 32 degrees of freedom. So the degrees of freedom within, you add up 32 plus 32 plus 32, you get 96. So there's 96 degrees of freedom. Notice this is very similar to the overall sample size, which was 33 times 3, which was 99. So the degrees of freedom within gets larger based on the number of participants in your groups, and the degrees of freedom between gets larger based on the number of groups that you have. So the degrees of freedom between reflects how many groups you have, and the degrees of freedom within reflects how many participants you have. All right, with these degrees of freedom, we have enough information to go to our F table and figure out what our F critical is. So there's a denominator degrees of freedom column. So our denominator, a denominator is the bottom of a ratio, so that is our within. So we have 96 participants in our denominator. So we'll look for that on our table. Well, it doesn't have 96, but there's a 95 and a 100. We can't use the 100 because that would be like having more participants than we actually have, so we have to go back up to the 95 in this case. And our significance level, that's our alpha, that'll be 0.05. Next we need our numerator degrees of freedom. Well, the numerator is the top of a ratio, so that's our between groups degrees of freedom, and that's 2. So we go over here, 2, we go to the 2 column, and the F critical is 3.09. 3.09. So we've got our F critical equals 3.09. Just like with a t-test, the next thing we're going to need to do is decide to reject the null hypothesis or to not reject it, to fail to reject it. And the process is the same using our critical values. So our observed test statistic, 44, is more extreme than our F critical. Therefore, we decide to reject. We reject the null hypothesis. We decide that our observed samples did not come from a world where they all had the same difficulty level. All right, so this data is very inconsistent with a world where they're all equally difficult. And the kind of sample means that we got here are not the kind of sample means that you expect due to random sampling from this kind of a population. And instead, they more likely come from different populations, which is what our research hypothesis suggested anyways, is that they're not equally difficult. So we've decided to reject the null hypothesis. And if we were just doing a t-test, at this point we could interpret our results by just comparing our sample means. And whichever sample mean is larger than the other one, then we would interpret those results as the populations having a similar relationship, where the population of that group would have a population with a larger sample mean. But here we have 3 sample means, and we don't know if these two are different from each other, if these two are different from each other, or if these two are different from each other. We don't know where the difference lies because there's too many sample means. We've just decided that the 3 means aren't exactly the same as each other. So there's an extra step for an ANOVA when you reject the null hypothesis to determining which means are different from one another. And this is called, so I'll say, if you reject the null hypothesis, then you do post hoc tests. Okay, so post hoc just means after this or after the fact. So you only do these after rejecting the null hypothesis. And what these are basically like t-tests that compare these 2 means, and then a different one that compares these 2 means, and a different one that compares these 2 means, and it gives us a sense of where any differences would lie in the population. Just like with a t-test, we also will want to be able to calculate an effect size. And for an ANOVA, it's not a Cohen's d, it's an eta squared, and for that we want to have what's called a source table. And actually, you can use a source table to calculate all of your different components of your F statistic. So we'll talk about that later on. And we'll also talk about post hoc tests later on. But once you've done the post hoc tests and calculated your effect size, finally you can interpret the results of your one-way between groups ANOVA. All right, so these ANOVAs are a little bit complicated, so I wanted to just recap the overall logic of how they worked. Right, so we're calculating our F statistic, and it's the ratio of 2 variances. The top is the one from between the group means, and the bottom is the one within the 3 groups. Right, and so this bottom one is really easy to calculate. You just take the variance of the first group, the variance of the second group, and the variance of the third group. Add those up and divide it by the number of groups. And if your sample sizes are equal across your groups, that's all the bottom is. Right? And this is how much variability you expect if the null hypothesis is true. right? Because this is one estimate of how much variability there is in the population, if the null hypothesis is true. This is another estimate, and that's a third estimate. So we're just averaging them together, right? And this is how much variance is actually observed between our three groups. Remember, that's what we're interested in, is if our groups differ more than we would expect if the null hypothesis is true. So to calculate this, what we did is we calculated the variance of our three sample means, and we went up by multiplying it by the sample size. So it was the reverse of going down to get back up from our sample means, back up to a population distribution, right? And this is the actual observed variance, whereas this is what you expect if the null hypothesis is true. Right? So an F statistic is just a ratio of two variances. One is based on how much our group means differed from each other, and the other one is based on how much people differed within our three different groups.